The last presentation we completed r's complement. In this lecture we will learn r-1's complement. For every number system we have two types of complement. First one is r's complement, and second one is r-1's complement. Let's talk about decimal number system. Base or radix r in case of decimal number system is equal to 10. R stands for radix, and if we talk about r's complement, then we have to find 10's complement, and if we talk about r-1's complement, we have to find 10 minus 1's complement, which means 9's complement. Very simple. If we talk about binary number system, then base or radix r is equal to 2. So we have 2's complement and 2 minus 1, 1's complement. For octal number system, base is equal to 8. So we have 8's complement and 7's complement. For hexadecimal number system, base is equal to 16. So we have 16's complement, 15's complement. And we write 15 as f. So we have f's complement. We already know how to calculate r's complement. In this lecture, we will learn r-1's complement. In the last presentation, whatever we have learned, we are not going to use to calculate r's complement. We will use r-1's complement to calculate r's complement. So this presentation is all about calculating r's complement again by using r-1's complement. So what are the steps involved? The first step is to find r-1's complement, and the second step is to find r's complement using r-1's complement. So let's start with it. If you remember the last presentation, r's complement was given by r raised to power small n minus n. This was the expression for r's complement, and r-1's complement is given by r raised to power small n minus capital N minus 1. So you have to subtract 1 from the r's complement. I can write this as r's complement. So we have r-1's complement equals to r's complement minus 1. If I add 1 on the both side, I will have r-1's complement plus 1 equals to r's complement. This result is very important, the most important result in this presentation. Once we have r-1's complement, we can add 1 in it and we will have r's complement. Now you might be thinking why we are calculating r's complement by using r-1's complement. Because in last presentation we saw there is borrow operations involved in r's complement. But in case of r-1's complement, no borrow operation is involved. So let me write this down. In r-1's complement, no borrow operation is involved. In r's complement, borrow operation is involved. And we want to avoid borrow operations because it will reduce our circuit, and also we have result in lesser time. So let's try to find out r-1's complement. Let's take one example for it. We have to find 7's complement of octal number 5674. This is what we have to do. I will use this formula. R is 8, so 8 raised to power 4. We have 4-digit number. Minus capital N is 5674 minus 1. 8 raised to power 4 is 4096, but this is in decimal and we want octal equivalent of it. So we will convert this decimal number to octal, and you will have 10000 in octal minus 5674 minus 1. 1000 minus 1 will give us 7777. Let's see how. 0 minus 1, 0 is smaller than 1, so we have to take borrow, and borrow is 8 in case of octal number system. So 8 minus 1 is 7. So we have 7777 as the result, and now we have to subtract 5674. Whenever you are required to calculate r-1's complement, start from this point. No need to perform these calculations, you can directly start from this point. In question, it is already given you have to find 7's complement, and the total number of digits in the number is 4. So you have to take 4 times 7 and simply subtract 564 from it. And you can clearly see, as it is octal number system, 7 is the largest number, and when you subtract 5674 from it, no borrow is involved. 7 minus 4 is 3, 7 minus 7 is 0, 7 minus 6 is 1, 7 minus 5 is 2. So 2103 is the answer and no borrow is involved. So it is good to calculate r-1's complement first and then calculate r's complement. Whenever you have to find r-1's complement, start from this point. Let's solve one more example. In this example, we have to find 8's complement of 5, 6, 7, 4. So the first thing that we have to do is to find 7's complement of 5, 6, 7, 4, and we have already calculated 7's complement. It is equal to 2103, and in order to find out 8's complement we have to add 1 in it, because here you can see r's complement is equal to r minus 1's complement plus 1. So I will add 1 in the result. 3 plus 1 is 4, 0, 1, 2. So this is 8's complement and this is 7's complement. Now we will move to last example of this presentation. We have to calculate 1's complement of 1101. You can use this formula, but I have already told you we are not going to perform these calculations. I will directly write 1111 because I have 4-bit binary number, and I will subtract 1101 from it. 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 1 is 0. So this is what we have, and now I want to calculate 2's complement of the same number. So I will add 1 in this and the result will be 1100. So this is the answer. This 0010 is 1's complement and 0011 is 2's complement. And if you remember the last presentation, we calculated 2's complement of this number, and lots of calculations was there because of borrow, but in this case no borrow is involved and we can easily calculate 2's complement. So this is all for this lecture. In the next lecture we will solve few more examples on 1's and 2's complement. So see you in the next one.